Our first question here deals with basicity of amines. So each one of these questions in part one has three different amines, and the question is to list them from most basic to least basic. So as I go through these, I'll use one as our most basic and three as our least. So we haven't done a lot of questions like this over the year. Most of the time when we've been looking at these types of situations, we talk about most and least acidic. Fortunately, if you remember what you've learned with that, this is very much the same, but from the opposite end. In general, things like electron donating groups that decrease acidity increase basicity, and things such as electron withdrawing groups that increase acidity will do the opposite for basicity. So in part A, we have aromatic groups attached to our nitrogen. And you can see we go from 1 up to 3 aromatic rings. Now, how does the aromatic ring help or not help us here? Well, recall that the lone pair on nitrogen, which is what gives it its basicity, can donate into the aromatic ring. So essentially, we're treating, at least by resonance, the aromatic ring as a withdrawing group. So as we said, withdrawing groups increase acidity, but they decrease basicity. So the more aromatic rings we have directly attached to that nitrogen, the more that nitrogen is going to donate that lone pair, and the less basic it'll be. Part B, we have a series of 3 different anilines. We have the methoxy group, which is a resonance donor. We have the nitro group, which is a strong withdrawing group. And we have the methyl group, which is an inductive donor. So the more donating the group is that's attached, the better job it does to increase basicity. Unless we end up in a slightly weird situation like we do in part C. So methyl groups are electron donating. And we actually went over this exact example in class. We said that the more methyl groups we add, the more basic something will normally get. And so that does definitely mean that the amine here with just a single methyl is the least basic. But because of an exception that we have here, the 3 methyl groups ends up being less basic than 2. And that's basically a steric issue. Because we keep putting more bulk around the nitrogen, it has less ability to add in the hydrogen. And then part D is just like part B. The ethoxy is very much like the methoxy. It's a good donating group, whereas the chloride, being a halogen, is a withdrawing group, and then the one with no substituent falls in the middle. All right, question 2, we have a couple reactions to look at. Parts A and B are reductive amination. Remember, that's where the amine adds to the carbonyl, forms essentially an iminium ion, and that immediately gets reduced by the hydride. And so we end up with a product where the nitrogen essentially replaces the carbonyl. And so that's going to be what we see in both parts A and B. Part C is one of our rearrangement reactions that we use to make amines from other functional groups. In this case, we use hydroxide and bromine to essentially remove the carbonyl from the amide and yield us a primary amine. And then finally, this set of questions ends with the synthesis question. We've got this tri-substituted aromatic that we're going to try and make from just benzene. So we want to end with benzene, and we need to put an alkene on there, a fluorine, as well as that amine group. So the question becomes, how are we going to do this? Because this is a lot going on, and we're just going to start, and we may hit some dead ends and have to backtrack, but that's part of doing a synthesis question. So when I look at this, I see that amine there, and my initial reaction is that I want to make that from a reductive amination. So if I had that carbonyl, I can add dimethylamine and then use the borohydride to make the product. Now from here I've got some challenges. I don't have a way to directly add an alkene, so can't do that yet. I'm thinking I might make it from a carbonyl, do a Friedel-Crafts acylation and reduce that and then do an elimination. But that's not going to help us yet. But that fluorine we need to add, and we know we can use that unusual reagent, xenon difluoride. And so let's see if that works. So if I do it like that, that's going to add a fluorine. We've got two possible positions that we can add it at. The one in yellow where we don't want it, and because it's symmetric, that would be the same as that position. And then we want it on the carbon I've highlighted in green. So now the question is, does our substitution pattern line up? So the carbonyl, we know that this is a meta director. And so the meta position to that carbonyl is our desired carbon. We know that the alkene over here is an orthopara director. And the orthopara is also one of those carbons I've highlighted in green. So that's going to work. The substituent that we add in is going to go onto one of those green carbons. Doesn't matter which one, they're equivalent because at this point the aromatic ring is symmetric. But that allows us to put the fluorine on. Now we've got to get two carbon groups on there. We've got the alkene and we've got the carbonyl. So I think at this point, most likely, we could use a Friedel-Crafts to put on the carbonyl at the top right. And that's specifically the Friedel-Crafts acylation. Now we've always said there's a couple things we can't do with a Friedel-Crafts. One are electron withdrawing groups. That alkene is definitely not withdrawing. And the second one is we can't have any amines present. Definitely no amines. So we're safe there. What about where it's going to go? So the alkene that we have, this group, we said a moment ago, is an ortho-para director. So that means it's going to direct new substituents, either ortho or para. So we're probably not going to get full para substitution, but there really isn't going to be a good way to do that, at least, especially not with the level of knowledge we have at this point um, in the course. So this is probably just one of those points where we say we're going to do this Friedel-Crafts reaction. We're probably going to get a mixture of ortho and para substitution, and we're just going to assume that at that point we can separate out the isomers and continue on our synthesis with the one that we want. So finally, to put that alkene on there, we could make that alkene from an alcohol using some sort of base. I'm sorry, not base, but acid to trigger the dehydration. We can make the alcohol from reduction of the carbonyl using sodium borohydride. And finally, we can make that carbonyl starting from benzene using a second Friedel-Crafts acylation.